Okay, so this is going to be our last section of acid-base notes. And in your notes book, this is page number 106. You will also need your reference tables because we are going to continue with reference table K, reference table L, and then now we're going to include reference table M. Okay, so I'm going to switch into my tablet mode and we're going to get started. All right, so I have the notes already filled in with my handwriting. These are my scanned notes, which are also posted to Google Classroom. And I'm going to just try my best to just work through these notes in the most efficient way that we can. Okay, so acid-base indicators. So this is what we have listed on table M. So we have an indicator, and an indicator is just any substance, and it's usually a weak acid that is going to change color based on a pH change. So it's something that's going to change color. It's going to kind of give you an idea of what the pH of a substance is if you use the indicator to test. And indicators are chosen based on the range for a color change. So you can tell if something is acidic or basic, really basically just a very general range, right? So remember, we're just going to do a quick review. When we talk about a pH, again, less than 7, we have the acidic range. And if we have a pH of greater than 7, we have our base range. And then remember, our pH of 7 is going to be our neutral. Okay, so we have two indicators here, phenolphthalein and methyl orange. So these are just the names of these two indicators. And phenolphthalein is something we're going to use definitely in the lab as a lab technique. And it's something that is colorless until it's met with something of a pH of 8, which again is the basic range because that's a pH above 7. So any pH above 8 is going to turn this colorless liquid pink. And so if I add this colorless liquid and it turns pink, that means I have a pH above 7. It doesn't tell me how much above 7. It's just going to say either above 7 or below 7. And then there's another indicator called methyl orange. And now this indicator is going to turn, is going to turn red if it has a pH of less than 3.1. And it's going to turn yellow. Let's go with our yellow. It's going to turn yellow above a pH of 4. And then if I'm having between a pH of 3.1 and 4.4, this indicator would be orange, which is what happens when you mix red and yellow. And so this is the basis of table M. And so now methyl orange obviously has a much narrower pH range than phenolphthalein, but it's not going to be able to tell you if something is a base or not, because anything above that pH of 4 is going to be one color, and it only can tell you some basic ranges. Okay, so now let's take a look at reference table M, right? So you should have your reference tables out already. Make sure you're taking a look at those all the time. All right, so we have methyl orange. So the way that this table works, and let me pick what color would I like to use. I like purple. Okay, so methyl orange. So then the first number goes with the first color. So 3.1 goes with red. So this means that anything below 3.1 would be red, right? So 0 to 3.1 would be red. And then anything above 4.4 would go with the second color, which would be yellow. And then if I'm just going to add another column over here for between. If I have something between 3.1 and 4.4, it's somewhere between red and yellow. So in the rainbow, what comes between red and yellow, or what happens when you mix red and yellow together, you get the color orange. All right, so then we're going to go on to bromothymol blue. So remember, the first number goes with the first color, the second number goes with the second color, and then in between, you mix the two colors together. So for this indicator, any pH value below 6 would be yellow, right? Any pH above 7.6 would be blue, right? That's how this goes. And then any color in between, yellow and blue. what color is between yellow and blue on the rainbow, or what happens when you mix yellow and blue together? We're going to get the color green. Now here's the phenolphthalein that we talked about, right? Which is going to tell you, which is our very important indicator that we're going to use in the lab. And we have 8 and 9, colorless to pink. Any pH value below 8 is going to be colorless, so clear or colorless. And then anything above 9 is going to be pink, so clear to colorless. And then it's going to be varying shades of pink in between pink and clear. All right, litmus is another important one, right? You may have talked about litmus in living environment or the litmus test, right? So litmus is going to be always red in an acid. I said acid, red, right? If I'm using my southern drawl. And then we're going to have blue in a base. B for blue, B for base. So any pH value below 4.5 is red. Well, acid is below 7, so definitely anything below 4.5 is an acid. So that, confirms our red for acid. And then any pH above 8.3 is blue. Any pH above 8.3 definitely is basic because it's above 7, so that goes with our blue for base. And then, of course, anything in between red and blue is going to be kind of like red, blue, purplish, but you're never going to be asked that. Bromocresol green, any number below 3.8 would be yellow. Any number above 5.4 goes with blue. And then between a 3.8 and a 5.4, yellow and blue mixed together, green, or between yellow and blue on the rainbow. Anything below 8, yellow. Anything above 9.6, blue. Anything between yellow and blue make green. All right? Not too bad. You cannot just pick, if I ask you what is the, the color of litmus at a pH of 8.5, you can't say red to blue because that's not an answer. You have to say one color. It's either red or blue, or it's the mixture between. And if I said, 8.8, well, that's definitely above 8.3, so it's going to be blue. If I said, what's the color of litmus at a pH of 4, at a pH of 2, well, I'm not going to say red to blue because it's not red to blue, right? It's going to be below 4.5, so red. Okay, that's how we're going to use this. So let's take a look at some of these. So I'm going to make my screen a little bit smaller so I can get that in there. And I'm going to erase my, answers here. And I would like you to, if I'm going to be able to erase, probably not, because it doesn't want to behave for me today. Okay, so it's not going to behave for me, so we're going to just leave all that writing on there. Okay, so bromothymol blue, pH of 6.4. So I'm going to go to bromothymol blue, and I'm going to change the color of my pen just to make it look a little bit easier. So what color will stand out against that purple? I think orange will clash really nicely. Okay, so bromothymol blue at a pH of 6.4. First find bromothymol blue, that's right there. And now 6.4 is right in between 6 and 7.6. So that means it's going to be between yellow and blue, which means I mix the two colors together, or what color is between on the rainbow? Green. Okay, so then now bromocresol green. We're talking about green. Let's switch to green. Bromocresol green at a pH of 5. pH of 5 between 3.8 and 5.4, so between yellow and blue, so green. And then we have pink for phenolphthalein 9.2, right? Because where's our phenolphthalein? Right over here. Right, here's our phenolphthalein. 9.2 is above 9, so then it's going to be pink. And then our methyl orange will be orange because 3.9 is between red and yellow, so methyl orange will be orange. So on the next page, on page number 107, I would like you to pause the video. I would like you to try these questions, and I'm going to have you answer them on the next page. Okay, So here are the answers. And we have yellow, yellow, colorless purple, yellow, yellow, red, blue, pink, red, blue, blue. Right? You should have paused the video and you should have tried these on your own. So for the sake of time, and so that you don't have to watch a super, super long video, we're going to go forward. All right, so now we're going to be moving on to neutralization reactions. But before we do, I want to throw in just a really quick review of what we have done so far in our acids and bases, right? So here we have our pH from 0 to 14, right? We have our H plus decreases as we go from 0 to 14. Oops, that's a plus. And our OH minus increases as we go from 0 to 14. When you're at a pH of 7, right in the middle, you have neutral. We have our acid range between 0 and 7, and you have your base range, right? A comes before B, right? So then the small end numerically of the scale is the acid, and the larger end of the scale is the base. So now we have two different acid-base theories, all right? So we have our Arrhenius theory, and then we also have our Bronsted-Lowry theory. And then sometimes this is referred to as the alternate theory because it explains some other things, explains some acid-base behavior that the Arrhenius theory does not explain. But both theories are valid. And remember, theory in science does not mean guess. Okay, so the Arrhenius theory is based on the H plus being the only positive ion in solution, and the OH minus is the only negative ion in solution, right? And then we have hydronium, is that H plus, and we have our hydroxide, the OH minus, right? And then again, table K and table L are going to have your Arrhenius acids and bases, right? That's our Arrhenius theory. So now with our Bronsted-Lowry theory, this is the alternate theory. It's the one that students don't like because it's harder. And that's why I like to call this the bad theory. Usually I do this around Easter time and, show like a little picture of a, cute little lamb or something. All right, so then what does that stand for? This is just a little memory trick that stands for bases accept and then acids donate. But what is getting accepted or donated? The H plus, right? The H plus, right? This is why pH is the power of hydrogen. Both of these theories incorporate the concept of that hydronium ion being extremely important. Okay, so bases accept and acids donate the H plus. And then that's where you have those conjugate acid-base pairs, which is really important. This is a very important concept in biology and also the environment. I'm just not going to write the word environment, right? And your body systems, right? Your blood is a Bronsted-Lowry base buffer system. Very important. Your blood is a very narrow range of pH, right? Because if your pH of your blood changes, it's detrimental to your health. Okay, so let's talk some reactions. Let's talk neutralization reactions. So what does neutral mean? Neutral means it's neither acidic nor basic. That means that the H plus equals the OH minus. So what do you think of when we think of the word neutral, right? We think of water being neutral. I feel like I should use blue since we're talking about water. So water is neutral, right? I have two hydrogens and an oxygen. But what is water? It's the H plus with the OH minus being equal, right? Two hydrogens and the oxygen, right? HOH. pH is equal to 7, right? So it's a scale from 0 to 14, right? And we have 1 times 10 to the minus 7, all the way up to 1 times 10 to to the minus 14, right? Where this number up here is your exponent if we're doing our logs. Okay, so what is a neutralization reaction? A neutralization reaction is when an Arrhenius acid, right, our H+, our hydronium ion, reacts with an Arrhenius base, our hydroxide ion, to form a salt, which again is an ionic compound. Remember, ionic compounds are a metal plus a nonmetal, and water. So we had that in the beginning part of our notes. If you take an antacid, like Tums is an antacid, it neutralizes your stomach acid. Your stomach has hydrochloric acid, and Tums is calcium carbonate. And that is going to neutralize your acid, and it's going to provide you a little bit of acidic relief, right? Because you're going to make a salt, which your body has anyway, and it's going to make some water, which is neutral. It's going to absorb some of that acid. So the general reaction is an acid and a base make a salt and water. And what happens is we have our H+ from the acid and our OH- makes our water, which I most of the time will be writing as HOH, because it's going to make for balancing easier, and it also shows you that the H is equal to the OH. Your acid ion is equal to the base ion in a neutral solution. And then where's the salt come from here, right? From Na with the Cl. Remember, sodium chloride is just one salt. So your H plus OH is going to make HOH. So this is on your reference tables, on reference table I. This is called a net ionic equation. Well, first of all, it's an equation because I'm adding two things together with an arrow, right? It's an equation. It's a chemical equation. So you have your HOH making water, and it's on table I. So your acid plus your base makes the salt plus water, which is neutral, equal H and OH. So remember, your anion is the negative ion, right? And then your cation. So your anion and your cation. So you have your H+ with the anion, and you have your OH- with the cation. And then this is how you have your H+, your OH- make the water, and your salt comes from the positive and the negative ions coming together, and then they're neutral. So acid-base neutralizations are it's a category of a double replacement reaction. And we always have to make sure we're using the right formulas when we write our acid-base equations. Remember your net ionic equation. This is also on table I of your reference tables. So the net ionic equation is very important, right? Your HOH equals water. So now let's look at how are these formed. So when I formed, I'm going to look for my H and my OH. The two on the outside go together. That makes your water, right? HOH. And then potassium goes with the bromine. Positive first, Br. +1 for the potassium, bromine is the -1. Where does that come from? That comes from your periodic table. Let's go quickly to our reference tables. I can show you quickly where that is, right? So let's see here. Potassium being a +1. And then we have our, I forgot which one we're looking at here. We are looking at bromine being -1. So then that formula is a correct formula. So now let's look at our next one. We have OH and H, 2 on the inside go together, 2 on the outside go together. So your HOH, and then is this balanced? Sorry, we should have made sure question number 1 is balanced. And the reason why I like to write HOH is because then I can balance the OH with the OH. So I have 1 OH, 1 OH, 1 potassium, 1 potassium, 1 bromine, 1 bromine, all set. So your H and OH make the water, and then you're going to get the sodium is going to go with this acetate ion from table E. Sodium is a +1 from your periodic table, and acetate is a -1 from table E. So now this is a correct formula. And so now I can balance the acetate ion as its own thing. Let me just, oh, apparently I can't, oops, I can't erase today. Oh, what a mess I'm making. Okay, I'm just going to forget to erase today. Somebody remind me not to erase. Okay. So let's go on to our next one, and that one's balanced. So this one is not going to necessarily be balanced, and this one looks a little bit different. Sorry, my handwriting on the scanned copy is a little bit messy. So we have our OH and our H, so then that's going to make water, so HOH. And then now I have a potassium is going to go with the PO4. So I have K in PO4. Potassium is a +1 from the periodic table, and then the phosphate is a -3 from table E. So in order for this to balance, symbols, right, potassium, the phosphate, charges, +1, -3. Now crisscross, right, because common multiple, I need 1 phosphate and I need the 3 potassium. So that's where I bring this 3 down. Now the reason why I like to write water as HOH is because it's going to help us balance it later. So let's do a quick balancing review. I need to keep track of potassium. I'm going to keep track of hydroxide. I'm going to keep track of my H, and I'm going to keep track of the PO4. So remember, when we write something as a polyatomic ion, it makes balancing a little bit easier. If you write your formula correct, the balancing should be easy. If you write your formula wrong, the balancing will never work no matter what you do. So now let's count how many we have to start with on each side. So I have 1 potassium, right? We're ignoring, let's just scribble those out and make my messiness even more messy. All right, so now I have 1 potassium, I have 1 hydroxide, I have 3 H's, oops, sorry about that. I have 3 H's, and I have 1 PO4. And now on the other side, I have 3 potassiums, right, because my subscript of 3. I have 1 OH, and then I have 1 H, right? This is why I write it as HOH. It makes balancing easier. And then PO4, I have 1. So right now, my potassium and my hydrogen are the ones that need to be balanced. So I need to make the potassiums on this side equal to the potassiums on this side. So then in this case, I'm going to make that a 3. So now my potassium is going to be equal to, again, with my a 3. And now I change the OH also to 3, right? Because remember, the coefficient multiply is everything afterwards. So now since I made this OH a 3, I want to make this OH a 3. So I'm going to put a 3 in the front. And so now that OH is 3, but I also changed the H to 3. And then now 3, 3, 3, 3, 3, 3, 1, 1. Now my equation is balanced. All right, so I'd like you to try the next one, but it's already written, so why should I bother? Okay, so +2 for the calcium and a -1 for the nitrate. So that's where that subscript comes from. Notice I do not take subscripts from one side to the other side. Subscripts come from those oxidation states, right, from your periodic table and table E. And then we balance this with an HOH. Okay, so then the H goes with the OH, and then the calcium goes with the nitrate. So now, do we always get a neutral solution? Well, first of all, it depends on how much you add. So there's too many variables at stake. But let's just say we did equal amounts. So if I combine equal amounts, so if I combine an equal amount of a strong acid and a strong base, I am going to get a neutral solution because the H will cancel out the OH, right? Your H plus and OH minus, if they're both strong, they're going to cancel each other out. But if I have a strong acid and I threw in this weakling base, an equal amount of this weakling little base, that weakling little base does not have enough OH to counteract and neutralize all that H plus. So you're going to end up with still acidic, and it's going to be a pH of less than 7. It's going to be less acidic because we added a base, right? Because if I add a base, the pH is going to go up, right? So it's going to be, your pH will go up when you add a base. And if I have a weak acid and I throw in a strong base, you're going to end up with something basic, but it's not going to be as basic because you added an acid, but you're still going to have a pH above 7.